guys, welcome to this crash course on topic 2 of Unit 1 Edexcel IAS Chemistry, which is the atomic structure and the periodic table. I will be explaining to you all about these 6 subtopics which comes under the topic 2 of Unit 1 Edexcel IAS Chemistry. Today I will be mainly focusing on the structure of the atom and isotopes, and also on mass spectrometry. So to start off with, this is basically a recap of the basics of chemistry of what we have learned since we were in grade 6, which is the structure of the atom and the isotopes. So basically, as we all know, there are 3 main fundamental particles which are known as the subatomic particles, which are the proton, neutron and electron. And the proton and the neutron is located in the nucleus, and the proton is positively charged whereas the neutron has no charge, and usually their relative masses are about 1. Then we have the electron, which is usually positioned in the orbitals, or which is known as the outer shell, and this word orbitals will come across it many times at the end of this lesson, where I explain to you all about the orbitals. Until that, let's just leave out the word orbitals and focus on that they are positioned on the outer shell, and then their relative charge is usually -1 since it's a negatively charged particle. Then we have the mass number and atomic number, and as we know, the atomic number is usually the number of protons in the nucleus, whereas the mass number is the total number of protons and neutrons in the atom. In order to calculate the number of neutrons, we can subtract the mass number by the atomic number. I have added a small diagram of the chlorine atom, where you can see how a 2D structure of the atom is drawn, which we have done many times. Here basically we see that the protons and neutrons are located in the middle of the atom, which is the nucleus, and then you have the yellow colored dots, which is basically the electrons on the outer shell. Moving on, we have the isotopes. So this is a very familiar topic, where isotopes. Basically, isotopes are atoms with the same number of protons but different number of neutrons, and they also share similar chemical properties because they have the same electronic structure, and also because they have the same number of electrons in the outer shell. Then we come across the term relative atomic mass, and the definition of relative atomic mass is that it is the average mass of one atom, which is compared to 1/12 of the mass of one atom of carbon-12. So this is basically a recap of what you all have learned so far. And then we come to an isotope calculation. So usually this type of question is given in our Unit 1 IAS paper for around 2 marks. So this is an easy 2 marks. So what we do here is that in this question, we have that chlorine has 2 isotopes, which is 35Cl and 37Cl, and 75% of the chlorine is 35Cl and 25% of the chlorine is 37Cl. So in order to calculate the relative atomic mass of chlorine, here what we do is we take the specific isotope and multiply its mass number by its percentage. So for example, we multiply 35 into 75 plus we do the same thing to the second isotope, which is 37Cl. So we multiply 37 by 25, and since 75 and 25 are a percentage, we divide the total by 100. So as what I have done here, where we have the average mass of the atom, so 35 into 75, and we add that with 37 into 25 and divide it by 100. So here we are able to calculate the average relative atomic mass of chlorine. So this is most of the time a very easy question to score 2 marks in. Then we come to something which is relatively new, which is the mass spectrometer. So So this mass spectrometer is used in order to always find the number of isotopes and its natural abundance or percentage availability. We use this mass spectrometer. I have attached a small diagram of a mass spectrometer where you have the several parts it's broken up into. So basically what happens, the first step what happens in a mass spectrometer is that the sample which is being analyzed should always be in the gaseous state. So in order for this sample to be in the gaseous state, we have the heater where it vaporizes the sample so that it is converted into its gaseous state, and it enables the particle to move through the mass spectrometer. So therefore the heater is used in order to vaporize the sample. In the second step what happens is this vaporized sample is bombarded with high energy electrons. Due to this bombardment of high energy electrons, the electrons will collide with the atoms of the sample, thereby one or more electrons are removed from the atom, which enables it to form its positive ion. So at this point, at the end of the second step, we have the atom in its gaseous state, but now due to the bombardment of the electrons in the second step, it is converted into a positive ion. So then in the third step, as you can see at the point where they have said that the ions are accelerated on the diagram, an electric field is used in order to cause this acceleration to the positive ion. And then in the fourth step, these positive ions are deflected by a uniform magnetic field as shown in the diagram. So the amount of deflection depends on the mass to charge ratio of the ions. So ions with a large mass to charge ratio are deflected less than the ions with a small mass to charge ratio. So for an example, there may be an instance where all of the ions have the same charge. So when this happens, we need to understand that the extent of the deflection is always inversely proportional to its mass. So that is the idea we follow when we talk about the amount of deflection which happens when the positive ion enters the uniform magnetic field. Finally, the final step is how this ion is detected. So the deflected ions will pass through a narrow slit, and they are collected on a metallic plate which is connected to an amplifier, which is basically the detector. So in order to identify how the strength of the magnetic field is then changed to detect the positive ions with other mass to charge ratios is not in our syllabus, so we are not supposed to know about it clearly, and usually in papers they don't test it as in detail. They usually test it by giving you a set of series of questions like why is the electric field used, or how is deflection occurred, why is the sample vaporized. Those are the basic questions they ask in in how a mass spectrometer works. So that's the style of questions they use. Then I have just simplified a small summary basically of how the mass spectrometer works and how a mass spectrometer works, which I have explained in the previous slide. Then we come to something called the mass spectrum, which is relatively new along with the mass spectrometer. So in this diagram is basically a diagram of a mass spectrum. So here you have this black bold vertical lines, which is basically showing the number of signals, or it's known as the number of signals. So this number of signals depicts the number of different particles which have different mass to charge ratio values. For example, here you have one signal for the mass to charge ratio of 24, Likewise, you have another one for the mass to charge ratio of 25. Then you have another one with the mass to charge ratio of 26. So this is basically the number of signals showing which is shown for different mass to charge ratios. Then on the left hand side of the diagram, we see on the y-axis the abundance. So basically you have the mass spectrum in order to show the amount of natural abundance of each of these species with different mass to charge ratios. So the mass to charge ratio of 24 has a greater peak because it is the molecular ion peak, and this is basically the peak with the highest mass to charge ratio in the mass spectrum. So then we have something called the M+1 peak. The M+1 peak is always the peak which is just on the right hand side of the molecular ion peak. So for example, in this case, the M+1 peak is the magnesium, the positive ion of magnesium with a mass to charge ratio of 25. So that is your M+1 peak, but 24 is your molecular ion peak since it has the highest abundance, highest percentage abundance. So this is how we interpret a mass spectrum. When we come across results of the mass spectrum, so for the results of the mass spectrum, what we do is we calculate the relative atomic mass of magnesium. So what we do here is that we take the abundance and multiply it by the mass to charge ratio, and we do that for the other signals as well which is present. So for example, we multiply 24 with 78.7, then we add the total of 25 into 10.13, and then again we add 26 into 11.17. So since all of this is a percentage, we divide the total by 100 and then we get the relative atomic mass. So usually the answer which we get for the relative atomic mass should be similar to the mass to charge ratio of the signal which has the highest abundance. So that is a way where we can check whether the mass spectrum and our results tally with each other or whether they are similar to each other. So for example, so this is the method of how you get the relative atomic mass of magnesium in this particular mass spectrum. Then you can be tested in another way, or there is another question where they tell you to draw the mass spectrum and then calculate the relative atomic mass of the element using the specific spectrum, and then they say you to identify the +1 charge species form. So in this question we have that chlorine has two isotopes, which is 35Cl and 37Cl, and 75% of the chlorine is 35Cl and 25% of the chlorine is 37Cl. So the question here asks us to calculate the relative atomic mass of chlorine. So there are three steps of how we do this. First we have to identify the +1 charge species, then we have to draw the mass spectrum, and then we calculate the relative atomic mass of chlorine. So in order to identify the +1 charge species found in the mass spectrum, we separate the +1 charge, or we separate the species into fragmented ions and molecular ions. So fragmented ions are usually the single ions, which is 35Cl plus and 37Cl plus. Then we have the molecular ions. So the molecular ions, what we do is basically, since there are two species here, which is 35Cl and 37Cl, so the two species could either be 35Cl or 35Cl, 37Cl, or 37Cl, 35Cl, or 37Cl and 37Cl. So here when we write the molecular ions, we have to always make sure that we write it in the form of a bracket, and outside the bracket we have the positive charge. If not, there is a chance that you would lose marks for not writing the molecular ion properly. So here, since there are two species, we can form 4 molecular ions. So after you identify the +1 charge species, then we try to calculate the mass to charge ratio of the specific molecular ions which we have found. So as you can see here, the 35Cl and 35Cl will form a peak at 70 since it has a mass to charge ratio of 70. Then likewise the 35Cl and 37Cl will form a peak at 72. And then 37Cl and 35Cl again forms a peak at 72, whereas 37Cl and 37Cl will form a peak at 74. And since that is for the molecular ions, so according to the fragmented ions, there will be a peak formed at 35 and 37. So the species which are responsible is shown in the table for the relative peak values. So basically, when we draw the mass spectrum, we will be having 5 signals at different mass to charge ratio, which is shown in the table. So then we have the structure of our mass to charge ratio, where it should contain 5 signals with the mass to charge, with its specific mass to charge ratio. So now the final step is to calculate its percentage abundance. So what we do is almost similar to what we did when calculating the mass to charge ratio. So in the mass to charge ratio, by using the molecular ions, we added the mass numbers together in order to get its mass to charge ratio. So in order to get its percentage abundance, what we do is we multiply the relative percentage of each ion. So in this case 35Cl plus has 75%. So therefore, since it's 2 35Cl plus ions in the molecular ion formula, what we do is we multiply 75 over 100 into 75 over 100. So thereby we get a percentage of 56.25%. So likewise we do the same thing for the other molecular ion formulas as well, and then we get the relative percentage abundance for each molecular ion. Then finally we can draw a final mass spectrum which would look like this, and it will have 5 main peaks because it has 5 signals. And then 3 of these peaks are due to the molecular ion peaks, which is due to 35Cl, 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 37Cl, and 37Cl, and 37Cl. And other isotopes we ignore. And then the natural abundance or the relative intensity is basically is the relative abundance which we have calculated. So 35Cl will have the highest because it is closer to the relative molecular mass of chlorine, which is 35.45. So therefore the signal which is drawn at 35 will have the highest abundance. Then finally we have the uses of mass spectrometer. So basically we use mass spectrometer for many different things, but most commonly it is used in drug testing and quality control in the pharmaceutical industry along with radioactive data. So this is some other extra uses of the mass spectrometer. And thank you. That is a small crash course of how a mass spectrometer is used and how we interpret a mass spectrum. And in the next class, I will be talking about the orbitals and the off-bar principle.